In this video, I want to do an example utilizing forces in circular motion. In particular, I want to look at banked curves. This is the problem of cars moving around in a circle, and if they want to move around in a circle at high speeds, how the curve itself is set at an angle then to help the car stay on the road. So to tackle this problem, I think we need to spend some time on the visualization stage. What does this mean? So I've got some road, I guess. So some curved road. I'm going to draw that road here. Not a very good road, but so some car then is on this road moving in this circle. And so, well, it doesn't necessarily have to be a circle, I guess. The angle, the radius of curvature might change as the car goes around, but at any particular part, there's going to be some radius of curvature due to this road. So I would say somewhere out here is the center corresponding to this sort of radius, this radius of curvature. And so I might draw a sort of an R unit vector from, an R vector from the center of this rotation out to where the car is. Okay, so that's sort of one way to look at it. I want to look at this idea of the banked curve then. So if I sort of look at the banked curve then, I have this is horizontal to the ground, and I'm going to call my banked curve some it's now at a slope at some angle theta relative to the horizontal. I'm now looking at my car which was going up in this in that picture is going to be going into the screen in this picture, so the velocity is sort of into the screen, and so it's going to look like this on my banked curve. Well, a very poor artist representation of what it would look like. Okay, and so what's happening with this? So if the car were at rest, presumably there's enough static friction between the road and the tires so that the car, is not going to slip down. So it's just going to stay stationary. So as the car speeds up faster and faster, eventually then if it goes too fast, we're told by the problem that the car could in fact start slipping up the slope. It's the same idea. If the car goes around too fast, the coefficient of friction is providing a force, it's keeping it on the circle. And so if it can't maintain that and going too fast, then the car slides off the road. And so if the car goes too fast, it can slide off the road, and in this direction it would slide up the slope. Okay, so I think we have a good visualization now of what's happening in the problem. We want to now move to the brainstorming session. What sort of physics applies to this problem, and what sort of relationships can we develop between all the subjects that we know. I haven't written them down yet, but we're assuming the car has some mass m. There's some coefficient of friction mu between the car and the road, and it's static. We're trying to see where it's not sliding. There's some radius of curvature. Remember of the road from this picture. We'll call that radius of curvature r, and then it has some speed, of course, v. All right, and so okay, so what can we use to to relate these parameters together? Well, we're going to use our forces, so let's do a force analysis on this. What sort of forces are on this object? Well, there's the gravity. We got to choose an object. Of course, we just have the one, so we choose the car. So, what are our forces? Forces. We have a gravity, which I'll call F sub g. And then there's a contact force then between the ground and the car. And we want to analyze the friction, so we're going to break this contact force into a normal force, which I'll call N, and then friction, which I'll call F sub F. All right, so these are the forces, and now I need a free body diagram. But again, this is sort of a complicated problem. So in what sort of coordinate system should I set up my my free body diagram? Well, let's look at these pictures. We know we're looking in circular motion. We want to utilize our circular motion relationships. And so in this picture over here, this is where it's moving in a circle here. I want to establish sort of my tangential axes, which is tangent to the circle, my radial axis, which is then radial to the circle. Here, how does that correspond to my this second picture? So in my second picture now, my radius, my radial axis is pointing out, and then my tangential axis is into the board. So that means my positive z-axis is up here. Again, I'm using a right-handed rule for a coordinate system. Index finger along R, middle finger along T. My thumb points up, which is in the positive Z direction. So, all right. So where are these forces pointing? Well, gravity's down. The normal force is going to be perpendicular to the surface from the agent to the object, and so that's sort of in this RZ plane in this picture. And friction then is going to be tangent to the surface. So I think I want to look at in this RZ plane to set up my my coordinate system, set up my forces. You can see without really good, in this case, really good and multiple pictures, it's really hard to come up with the right free body diagram and the right coordinate system in which to analyze these things. And sometimes you might just have to set up one. If it's not clear, set up one and go with it. And if it doesn't lead you to the right relationships, back up, go back to your visualization step, go back to your pictures and see if there isn't another perspective to look at the problem that gives you a different set of coordinates, a different coordinate system that you think might lead in a different direction, that might lead you to some useful relationships. Sometimes it's a trial and error if you don't know exactly which way to go. Okay, so I think I want to use this sort of perspective. So I'm now go to my free body diagram, which starts with a dot, and I put on my my forces. So my force due to gravity is down. My normal force points perpendicular to the surface, so that's off in this direction. Now the force due to friction. Well, I have to be a little careful about that, but let's get some axes on here. Whenever I've got things on an angle, so my purple here, this is purple is perpendicular and parallel to the ground. And then I have yellow is perpendicular and parallel to the surface. So I always get all all of the axes on my free body diagram, all of them, because then I can go to my picture and see where's my theta. That's what I know. Where does my theta correspond to these axes on my free body diagram? That's theta right there. And so once I have theta here, now I can identify theta everywhere else, because that's every alternating angle once I have all these axes drawn. So now I know where theta everywhere is. And so next, I need to know where the frictional force is pointing. So this is good. We already talked about this back in the visualization step. So if there's no friction, then if there's no friction, the car doesn't have a hope of making this turn, and it just shoots off. Just like if there's no friction, then this car just goes. I did that wrong, didn't I? That was bad. If there's no friction, the car just goes straight. That was a bad visualization there. That happens to all of us sometimes. And so it simply can't make that curve. It doesn't, of course, go off to the right. There's no force there, but it goes straight, and it can't make the curve. So what that means is from this point of view, if there's no friction, it's going to be moving that direction as it tries to make this turn. And so that means the force due to friction is in the opposite direction of the motion of the object relative to the agent, and that's what I've drawn here. So the force due to friction is going to be along this direction. Okay, so now I have the direction of my forces, and now I want to, I haven't set up a coordinate system. What coordinate system do I want to work in? Well, I want to work into this radial RTZ coordinate system at this point. And so how does this translate from my my picture to my coordinate system, my pictorial representation to my sort of graphical representation? Well, a schematic really is a better way to say it. Okay, so this says, if I want to map it here, that this is my positive R direction, and then this is my positive Z. See, it would be almost impossible to come up with that with just going straight to a free body diagram without having spent some time visualizing what's going on in the actual system. All right, but so now that I have a set of coordinates, I can now vector sum my forces. All right, so first my normal force. So I want to find my normal force on my R and Z. Oh, before I do that, so if you look at this, think about this for a second. Previously, whenever we had sort of wedges, we were looking at wedges, we almost always went to coordinate systems that were parallel and perpendicular to the wedge. And so I can tell you, I've assigned this problem a lot of times, and a lot of students, when they see a wedge at this point in the course, they always go to a coordinate system then parallel and perpendicular to the wedge. But in this problem, that's exactly what you don't want to do. You want a coordinate system that's parallel and perpendicular to the ground. Why is that? That's because there's no net force parallel to the surface. The forces are in this RZ plane, and we want to know where this object, which is the car, does not move relative to the surface. In fact, the net acceleration is going to be along R. And so we want our coordinate system in such a way that we have only one axis along the direction of the acceleration. And so, just because you have a wedge doesn't automatically mean you want the axes parallel and perpendicular to the surface of the wedge. It all depends on the context of the problem. All right. So the normal force, we want the components along R and Z. And so I've already noticed that this is theta. And so the component along R is going to be the normal force times sine theta. That is the length of this side of this triangle here. The hypotenuse is the magnitude of the force, and so this side is n sine theta. This is along the r, and now I go to my coordinate system and I see that this is in the negative r direction. R is over here, so this is negative r. All right, and so now I want the length of this side of this triangle along the z-axis, and so that length of that side of that triangle is n cosine theta. That's along the z-axis, and it's looking at the diagram is in the positive z direction, and there's nothing along the sort of tangential to the circle. So that's there. The force due to friction, then, I also need to find components perpendicular on the r and z axis, and again, I have already identified that to be theta. So the magnitude of the frictional force in my frictional force model is mu n, and so the component along r is mu n cos theta along r, and looking at my diagram, it's in the negative x direction, just like n. You know, if we've forgotten, here's the force due to friction, here's my normal force. And so for both components along r are in the negative r hat direction. So it also has a component along z. The magnitude, again, frictional force in our contact model is mu n. And so the length of the triangle right here, which is along the z-axis, is mu sub n sine theta z. And from my coordinate system, from my picture, it's in the negative z direction. It's this direction, and positive z is up. My component is pointing down. And finally, I have the force due to gravity, which has nothing radially. Its magnitude is the mass of the car in the z direction, and from my coordinate system, I see that's negative. All right, and so I can now add these forces together, which give me the mass of my car times the acceleration of my car. And since I've chosen a very convenient coordinate system, I know that given that I'm looking for the condition, sort of the maximum condition where it's stationary, there's no acceleration along z, and I just have the mass times the centripetal acceleration or radial acceleration along r. So that gives me these relationships to work with. And so that gives me that, looking at this one first, gives me that n cosine theta minus n mu sine theta is equal to mg, where minus mg is equal to 0, g is equal to 0. So if I sort of pull out a factor of n here, I get n cos theta minus mu sine theta is equal to mg. And so this one here gives me negative n sine theta minus mu n cos theta is equal to ma centripetal acceleration. So let's work with this a little bit. I want to sort of say I'm trying to find the maximum speed, right? And so I know the maximum speed is related to my centripetal acceleration. So let's work with that first. So given this, I know that I'm going to factor out a factor of n sine theta plus mu cos theta, I'm bringing a minus sign on the other side, is equal to m v squared tangent over r, where here v tangent is the speed of this object and r is the radius of curvature, the magnitude of that radius of curvature of the road. Okay. And this was minus. This is originally minus, and I got that minus to subtract out these minuses that were there. And so now I have this relationship. And looking at this, and that's one of the advantages, it helps as long as you keep all your parameters out, you don't plug in numbers too soon. It often gives you the right insight into how to solve these systems easily. If I look at this and I look at this expression, I'm just bring these two together. It becomes really obvious on how to solve them. Minus mu sine theta is equal to mg. I'm simply going to divide these equations. So, I could solve this one for n and substitute it in there. That seems really cumbersome. I can just divide these two equations. The n's cancel, the m's cancel, and I get this sine theta plus mu cosine theta divided by cosine theta minus mu sine theta is equal to vt squared over gr. So now I can solve for, should I write that out? Sure. Sine theta plus coefficient friction cosine theta minus mu. No reason to skip steps. It's not too difficult. Squared over gr. So now I can solve for my final answer. My tangential velocity is going to be gr times the ratio sine theta plus mu cos theta over cos theta minus mu sine theta, and then square root. So I want to check this answer. I see my units are right. I have the square root of gr, which I know is a speed. This is all dimensionless, so I have the units right. Both the sine and this term right here, both sine theta plus mu sine theta, these are the components of the normal force as well as the force due to friction, which are both helping keep me on the circle. And this term here corresponds to the normal the combination along the z-axis that contribute to the normal force. And so this is the from what I can see right away, looking at the checks, this seems to make sense. And so here we have the speed given for a banked curve, the maximum necessary to keep it on the curve. And really the final equations, it seems like a lot of terms, but there's really very little algebra involved in this. But the main difficulty with this one was the setup and making sure you had the right visualization, the right picture, the different perspectives that allows you to set up your free body diagram with the right coordinate system that lets all of this fall out. So a lot of times if you have a problem, you just can't skip the brainstorming session. And it brings up another thing that we'll see over and over again. The time that you spend on the visualization step saves you so much time in the end. Now this problem, I went pretty slow to work out all the steps. It just simply to solve it does not take a lot of time. But what takes a lot of time is not getting the visualization step and then spending maybe even in fact hours in a massive algebra trying to understand what happened, what went wrong. The bit of time that you spend in the visualization step saves you so much time in solving more complicated problems.